Hello all and welcome. Today we are having a talk by Kun Zhang from CMU on methodological advances in causal representation learning. Our discussant will be Veitch from University of Chicago. And yes, apologies for starting a little bit late. Ying will handle the questions today, so I will pass it on to her so she can inform you how that works.
Thank you, Emma. So as usual, please submit your questions through the Q&A section. If you haven't used it before, it is just a button at the bottom of the Zoom window. So please submit through the Q&A instead of chat for us to better track the questions. And that's it. Without further ado, the stage is yours. Please feel free to take over, Kun.
Yes, please feel free to share your slides.
Oh, I think I got disconnected for 10 seconds.
Oh, you can share your slides now.
Okay, wonderful. So should I start? Oh, sorry, I got disconnected.
No
Okay.
worries. You can start. Yes. Thank you, Kun.
Okay, thank you very much to Emma and Ying for the invitation and organization. So I'm very glad to be here to talk about some recent methodological advances in causal representation learning. So here, everyone is familiar with causality. So let's directly see the essence of the talk. We know that with almost the same dependence pattern between the two variables x and y, different causal models or causal relations between x and y will give rise to different distributions under manipulations. For instance, if x causes y here, then we know that the causal effect of x and y would be the distribution y given x, right? Very simple. And if y causes x instead, then the distribution y under intervention x would be py, the original py, because intervention does not change x at all. And similarly, if they have a latent common cause, z, then in this case, the distribution y given the manipulation on x will still be the original distribution y. So now you can see clearly there's a difference between the statistical dependence and causal influence or causal relations. And in this talk, we are going to see how to discover the information of causality and make use of it in some situations. Here, I would like to give some very quick example to illustrate why we want to learn causality. So in the first example, the classical example, if you want to change the incidence of lung disease, clearly you care about not just the correlation, but the causal relation. You want to change the causes. In the second example, which is known as the example of symptom paradox, we know that when we make recommendations, we care about not dependence, but only the causal influence of treatment on recovery, right? And this causal influence could be totally different from their dependence patterns in this case, because of the existence of possible latent confounders. In this example, you can see 50 years ago, female students, college students were smarter than male students on average. Why? Because of selection bias. So gender and IQ were both causes of being admitted to college. And given that you are considering only college students, gender and IQ are dependent in some way. As a consequence, you could see very different patterns compared to the whole population. Okay, so if you want to go from the selected sample to the population, you have to have this causal picture in mind, and then can try to infer the information of the whole population. In machine learning, very often times we care about causality and how the distribution changes. For instance, in domain generalization or domain adaptation, we want to do adaptive prediction given the distribution. So in this case, clearly you care about how the distribution changes, right? And then you can either do adaptive prediction, or in some situations you can try to discover the representation that is actually invariant, and then you can make a robust prediction. In any case, you care about how the distribution changes. As I just explained at the very beginning, very often we can just consider different distributions as consequences of different, say, manipulations. And similarly, For AI diagnosis system, we care about not only the final diagnosis result, but also why, right? We would like to see what mutation caused the disease and how you can treat it. So we care about why and how. Similarly, in the recommended system, we care about not only what items to be recommended, but also why this particular item is recommended. Was it because the company would like to maximize the profit, or maybe was it because the company would like me to be better in the future, right? So you care about the goal or purpose of recommendation, and you want to see how to go further depending on the different purposes. Right here at the bottom, you can see a very traditional or typical example to illustrate the problem of adversarial attacks. Here you can see a panda, but if you add noise of a particular pattern or change the pixel in particular ways, then the machine may say it's something different with very high confidence. So why could this happen? Basically, you can mathematically prove the following thing. If machines actually learn and make use of different set of high-level feature representations than we do, then we can always change the input so that the machines and the human beings will learn different feature representations. And as a consequence, the decision would be different, right? So given that gap, you may wonder why, how to deal with the problem. And to answer this question, first of all, you want to see what kind of representation we make use of, right? So roughly speaking, we make use of generative features or causal features to understand the external world. Now, to make it more specific, why do we need causal representations? First of all, we can answer why questions, and second of all, as illustrated by a lot of empirical results, this kind of representation can benefit downstream tasks. Right? You can have this. You can try to derive this representation, and then you can do few source learning and so on. So in computer vision, there are a lot of results in this way. Some other people may say, oh, I would like to recover the true property of the generation process, right? That's also good. Even if you don't believe that the true process is really kind of causal, this metaphysics, actually Kant's metaphysics may be useful. So our goal is to make sure that the machines and human beings can communicate with each other without any difficulty, right? So we have to understand what kind of representation we actually rely on. According to Kant, this is right here, we have the world of experience. We can only perceive this world, right? And this world is produced by two things. One is the world itself. We cannot, unfortunately, we cannot directly access this world. Whenever we perceive something, we always apply our kind of pure forms of experience. So this is our perception system. Whenever we see something or feel something in our world, we already have all those pure forms. Those pure forms include a concept of space, concept of time, causal order, and so on. In other words, when we try to analyze something, it always builds in causality, right? And then if you would like to make sure the machines can think in the same way, then we have to make sure that machines can also discover and make use of the causal signal in the data. By the way, I learned this representation or this interpretation from Clark Glimmer, who is a philosopher. So in any case, even if you don't care about the true process, in order to make sure the machines can communicate with us seamlessly, you care about causal representation, right? Okay, now the problem is how we can go from data to the causal representation. In other words, what kind of footprint of causality can we discover in the data? So here, to answer this question, we have to have a look at the two issues. First, what property the data can be useful to discover causal information, right? And the second one is about the identifiability. So under those, we have to show whether whether the information that we can discover from data is strong enough so that we can recover the underlying representation uniquely, right? So first of all, let's have a look at the property of a causal system. Essentially, we make use of the modularity property of a causal system. Here you can see rain causes the wet ground, causing slippery. Although all those variables in the system can be dependent, By modularity, we mean the following thing. We can just divide the whole system into a lot of modules. Each module generates one variable from its parents. Although those variables are related, the modules are not related to each other at all. So they are irrelevant to each other. In other words, you may change one of them without changing any other module, right? And if all of them change, the change would be irrelevant or independent from each other. And then as a direct consequences of the modularity property, you can derive some statistical properties of the distribution of the data. So the first one would be conditional independence relations among the variables. Here, for instance, if you are given wet ground X, then Z and Y will be conditionally independent because X is involved in the generating process Y. If you fix X, then no matter what value Z takes, you don't care. In other words, Z and Y will be conditionally independent given X. So this is known as a Markov condition or called Markov condition. Okay, this is the first condition. And second one is independent noise condition. So here you can see E is the error in the generating process from X to Y. So E is basically involved in the second process right here, but X is produced by the first process from Z to X. So the two processes are not related to each other. As a consequence, X and E assume there are no other latent common code for X, Y. Then the error term or noise term in Y will be independent from X. So this is known as the independent noise condition. And the last one is a principle of minimal changes and independent changes. So as explained before, if you have a single change in the system, right, then the multiple distributions may have different distributions. Multiple variables may have different distributions. However, if you use another or alternative representation to encode the relations among, say, X, Y, Z, you are going to suffer more changes. So let me give an example. Suppose you only have actual changes in Z. Here you have changes, right? And then you can see, although distribution of Z changes, Tx given Z is the same, and the distribution Y given X is still the same. You have a lot of constraints. And then if you use the wrong causal representation, say, suppose you believe X cause Z cause Y. Now you can see, since distribution of Z given X is different, this is different, and we also know that the distribution of X will be different. So here you have one change, and similarly, the conditional distribution of Z given X will also be different. So you have to encode the two changes in the system if you have a wrong causal representation, right? And furthermore, we know that if we have multiple changes in the causal system, those changes in different modules will be independent from each other because they do not share any information. So this way we have the principle of minimal and independent changes in non-stationary environments. And later you can see each of those three conditions can just lead to some methods for causal representation learning. Okay, so this is the first question. And the second issue is about identifiability. We'll show that under some assumptions, each of those conditions can lead to identifiable representations. So here by identifiability, I mean, it's clear that the original causal representation can be recovered up to some indeterminacies you are aware of. So in some cases, there's a Markov equivalence class. In some cases, you can recover the underlying representation uniquely. And here, I would like to draw the connection between causal discovery and causal representation learning. Causal discovery is the task of discovering the underlying causal structure or causal model by analyzing observational data. It's quite a general problem. In causal representation learning, usually we focus more on the latent variables. So you may just observe a lot of low-level raw variables, and then you know that those low-level raw variables were generated by some high-level latent variables, and latent variables may be related. So in this case, you want to recover those high-level latent variables and their relations. So here I consider causal representation learning as a subtask of causal discovery with a focus on the latent variables and their relations. Okay. And then we can consider the setting of the problem. Essentially, we can consider three axes of the causal representation learning problem. The first one is what kind of data we can make use of. In some cases, we only have a single distribution, right? or we have i.i.d. data, and then we have some approaches. And in some cases, we can benefit from the some kind of parametric constraints on the causal influence. So this is the second axis. The last one is whether we allow a lot of latent confounders in the system. So here you can see, we have a closer look at this problem by considering each setting corresponding to different settings of the three axes. Okay, so just saw why we care about the causal representation learning. Now let's start with the i.i.d. case, where we have a single distribution, or we have just observational data follow the same distribution. Here you can see a summary of the recent methodological advances in causal representation learning. So in the i.i.d. case, right here, we may or may not have parametric constraints on the causal influence, and some approaches allow latent confounders and some do not. And you can see that generally speaking, we can recover the underlying truth or underlying causal representation up to the equivalence class. And in some cases, because of parametric constraints, we can recover the underlying representations uniquely. And after that, I will talk about non-i.i.d. situations. Okay, let's start with the i.i.d. situation with examples. So here you can see a data set collected by Mali Novak, my collaborator. So in archaeology, they really want to see why people in different areas look different. So she collected 250 skeletons, and she measured a lot of variables, including sex, cranial size, diet, location, climate, and so on. So essentially, now in order to understand why we look different, we have to see the causal relations among those features. And clearly in this case, the relations among those features could be very linear, very nonlinear, then we have no idea about it. And some variables could even have very high dimensions. For the cranial shape differentiation, about this shape, the dimensionality is very high for this variable. In this case, we can directly make use of only conditional independent relation in the data. And we have a single set data set, right? So we have i.i.d. data. And right here, let me just illustrate how the constraint-based method for causal discovery works. So essentially, here by constraint, I mean conditional independent constraints. So from data, we can discover conditional independent constraints, and then we want to find a DAG or set of DAGs to satisfy those constraints. So let me just start with the PC algorithm. PC stands for Peter, Clark, Peter Swerted, and Clark Limmer. So here we have data. From data, we can discover a set of independent conditional relations. And then you can show that under Markov condition and faithfulness assumption, two variables are adjacent in the causal graph, if and only if they are always conditionally dependent, no matter what variable you condition on. So now, since 1 and 5 are conditionally independent given 3, we can just remove the edge. And since 2 and 4 are independent given 1, we can also remove the edge between 2 and 4 and so on. So after this stage, you see we have a so-called skeleton without any causal direction. And then we want to find the direction. So since x2 and x4 are independent given 1, but not any variable set containing x3, we know the causal relation must go from x2 and x4 to x3. Otherwise, if that's not the case, then you can see that without the condition of x3, x2 and x4 shouldn't be conditionally independent. So we discovered so-called V structure right here. This is the V structure. And then we know that x2 and x4, x2, x3, and x5 is not a V structure. Then we can go this way. Otherwise, we are going to have a fake V structure. So essentially, you can find the causal skeleton and the directions for some of the edges. And of course, in this example, we can see two issues. First of all, we cannot see the direction between x1 and x2 and the direction between x1 and x4. We don't have such information. Later, you can see if you are willing to make some rather mild assumptions, you can just directly determine the direction between two variables. The second thing is that in the PC algorithm, it's assumed that there are no latent confounder in the system. And under that assumption, together with faithfulness and causal Markov conditions, you can show that asymptotically speaking, the result by PC is correct. What if you have latent confounders? And in reality, we always have latent confounders. So the second issue is how to deal with the latent confounders. Here you can see the result on the archaeology data by analyzing only the data by applying PC on the data. So you can see we can really discover the causal relations among those features. For instance, geodistance is the cause of climate. Climate is the cause of cranial size and cranial shape differentiation, and so on. So now we can really understand the process, and we can try to make changes under some. We can try to make some controllable changes. For instance, suppose you still want to eat something, right? You want to eat something, but you don't want the very bad effect of a diet. So you still want to preserve the same cranial shape differentiation. What can we do? We know that the causal influence of diet on cranial shape differentiation takes place via another two variables. Then we can just eat the same thing, but at the same time, we can try to protect our teeth, right, in some way to avoid the bad effect of the action. If you know the causal picture, then you have freedom, right, regarding how to make changes and how to prevent very bad effects from happening. Okay, now let's see how we can deal with the latent confounders, even with only conditional independent relations. But this is a part of the FCI algorithm. Let me just illustrate the ideas with two examples. In the first example, we have independent between 1 and 2, and conditional independent between 1 and 4, giving 3, and conditional independent between 2 and 4, giving 3. Now, if you apply PC, you get this result. 1, 2 are not adjacent, 1, 2, 3 form a V structure, and so on. So now the question is whether it is possible at all to have latent confounders behind X3 and X4. In other words, do you think it is possible at all for you to have the C variable here? Generally speaking, we can have latent compounder everywhere, right? So intuitively, immediately the answer could be yes, right? And then you realize the following thing. If we have such a C variable right here, then this path, X1, X3, C, X4 will be open if you condition on X3, right? Because here X3 is the collider for X1 and C. And as a consequence, on the faithfulness assumption, X1 and X4 will not be conditionally independent given X3, but will observe the conditional independent between 1 and 4 given 3. Contradiction, right? So what that means, it means that if faithfulness assumption holds true, then in this case, we definitely don't have the latent compounder between X3 and X4. In other words, in this case, we can get to know that between some pairs of variables, there are no latent compounder. And furthermore, in this case, we know that X1, X3 must be a direct cause of X4. So this is very informative from data, right? We can know there are no latent compounder. And furthermore, we know one variable must be a direct cause of some other variable. It's very, very nice. And you can apply this idea to a lot of problems, even in our everyday life. For instance, if X1 is a rain, X3 is a wet ground, and X4 is slippery, then you can see because of the conditional independent between X1 and X4 given X3, and because we know that the causal direction cannot go this way because of, say, temporal information, then we can immediately conclude that X3 must be a direct cause. It's not possible. X3 must be a direct cause of X4 without the latent compounder, right? And you can just apply this kind of idea to do causal analysis in history, right, and social sciences. Okay, so this is the first example in which we are sure that there are no latent compounder. Now let's look at another example. Again, we have 4 variables. So here, 1 and 3 are independent, 1 and 4 are independent, and 2 and 3 are independent. Good. Now, if you apply PC, you see, oh, since X1, 1, 3 independent, 1, 4 independent. So first we can find a skeleton this way. And then since 1 and 3 are independent and 1 and 4 are independent, we know here we should have a V structure. And since X2 and X3 are independent, we should have another V structure here, right? So now you can see contradiction. On the one hand, X2 should be effect of X4, and on the other hand, X2 should be cause of X4 at the same time, right? Why could it happen? Basically here, there must be latent confounders for X2 and X4. And furthermore, you know that in this case, there are no direct causal influence between X2 and X4. Because if there are any direct causal influence between X2 and X4, say the influence from X2 to X4, then X1 and X4 will not be independent on the faithfulness assumption. Okay, so in this case, of course, you can condition on some other variables as well, right? But in this example, you can see that in some other situations, we know that the dependent variables are not directly causally related. Instead, the dependence is caused by some latent confounders. Okay, and similarly, you can find a lot of applications of this idea. For instance, let X1 be whether I'm sick, X2 be whether I'm in this Zoom meeting room, and X4 be whether you are in this meeting room, and X3 be whether you are sick. Now you can just verify those relations, condition independent relations, and then although the conclusion that as follows, although both of us are here, right? X2 and X4 are clearly dependent in this case, we know that neither of them is the cause of the other. Instead, we are here because of some latent common cause. It's this seminar, right? So you can apply this idea to solve a lot of problems in practice. So with those examples, you can see that even with only condition independent relation, we can still say something about confounders, right? And if you want to see more details, you can have a look at the FCI, fast causal inference algorithm developed by Peter Spertis. Okay, the other issue is how to determine the causal direction between two variables. Previously, we only made use of condition independent relations. If you are willing to go further, actually, you can immediately see that we can make use of additional information, right, to discover causal information. So here, we just make use of some assumption on causal influence. For instance, if you assume the causal influence from cause to the effect, follow the linear non-Gaussian model, all of a sudden, the wrong direction will not follow the same property of the data of the model. So essentially, you can see, suppose X cause Y right here. Then when you try to explain Y with X, you can find the independent residual, right? This is basically the way to recover the underlying true process. The residual was independent from the cause. However, if you do the same thing in the reverse direction, right? Now you can see, although the residual of regression X on Y, regressing the cause on the effect, is uncorrelated from the predictor, they are clearly dependent, as you can see from the scatter plot. So the distribution of EX clearly is sensitive to the location or the value of Y. In other words, EX, the residual, and Y are dependent. So if you do not have the correct causal direction, you will have a dependence between the residual and the hypothetical cause. So this gives rise to the asymmetry between two variables. In other words, you can find the direction between the two variables. The same thing happens even if you have nonlinear functions. So that happen to post-nonlinear causal model and additive noise models. Essentially, as long as you are willing to introduce some rather weak structural constraint on the causal influence, you can see this kind of asymmetric information. Let's have a look at the post-nonlinear model. Right here, the effect is the nonlinear distorted version of the nonlinear effect cause plus some independent noise. This function, the alpha function, Fi2, could be very important because in reality, very often times we have sensor distortion, measurement distortion, because we have to use instruments to measure the underlying variables. So you can see linear model and nonlinear additive noise model are special cases, and even the multiplicative noise model is a special case. You can just rewrite the multiplicative noise model this way, and then you can see this is the post-nonlinear transformation, and this is the inner nonlinear function, and this is the noise term. So this model is rather flexible. However, even for this, for data generated by this rather flexible model, we still have the causal asymmetry between the cause and effect. As you can see from this example, here is one of the Tübingen causal effect pairs. We have two variables, x1 and x2. We have a lot of these data points here. And then, first of all, you can assume x1 causes x2. We have no idea what x1 and x2 are. And if you assume x1 causes x2, you can fit the model. You can estimate nonlinear functions and the error term in the model. Now you can see the error term is independent from the hypothetical cause. And then you can just consider reverse direction. Under the hypothesis that x2 causes x1, you can estimate the nonlinear functions and the noise term. And in this case, you can see they are not independent, really. And then we can conclude that x1, the model, post-nonlinear model would favor the causal direction from x1 to x2, because in this direction, the model is very simple. You can find the independent error term. In fact, x1 and x2 are altitude and precipitation of 300 cities. So clearly, we would prefer to have x1 as a causal, as a cause of the process. So here you can see some theoretical guarantee. Causal discovery is slightly different from other problems in machine learning. For instance, if you care about prediction, you don't really have identifiability, right? As long as you can make very good prediction, it's good enough. But in causal discovery, you cannot allow any mistake that you don't know, right? In other words, we have to make sure that the discovered information is really consistent with the underlying truth under our assumptions. So we conducted some investigation, and then by solving some differential equations, you can see that in only 5 specific situations, cause and effect cannot be distinguished. That means that even for the wrong direction, you can still find an independent noise term. The first one is very well known. It's a linear Gaussian case. But basically, each of those 5 situations is very specific. In other words, you have to tune the nonlinear functions and the distribution of variables very carefully so that one of them holds true. Okay. In other words, generally speaking, causal direction is identifiable if the data were generated according to this rather flexible model. And since linear model and nonlinear additive model are special cases, this identifiability result also applies to the data generated by those models. So now you can see, if you make some assumptions on the causal influence or causal mechanism, then you can discover causal asymmetry information even without making use of temporal information at all. Okay, and then let's go further. We know that in reality, we may have a lot of confounders. So let me just give a problem definition first. In psychometric studies, we can measure a lot of variables, right? There can be, say, answer scores. And then we believe that all those answer scores to different questions are dependent. They are not directly causally related. Instead, they were generated by some latent mental conditions. The latent mental conditions may be causally related. So now the problem is how to recover the latent world, or the world of latent variables, consisting of where the latent variables are and how they are related, by analyzing only the measured variables, xi's, right? So now you can see, actually, we can solve this problem in multiple ways. In 2006, Ricardo Silva and Clark Limmer and Richard Shines and Peter Svertis published a paper on the tetrad condition-based method. And recently, we developed a gene-based method. By gene, I mean generalized independent noise condition. So with this condition, we can immediately figure out where the latent variables are and how they are related. And it's easy to verify the gene conditions because gene conditions is just about the independence between the combinations of the measured variables. So in this case, we have a lot of measured variables right here, xi variables, and then gene condition is, we say yz, 2 sets of the measured variables satisfy the gene condition if there exists a non-zero linear combination of the y variables that is independent from z, right? We can verify this relationship relatively easily. And it's nice that this condition has a graphical interpretation. If this condition holds true, then we can say that the exogenous set latent variables of latent parents of y variables, d separates y and z. Now let me give an example. So for instance, if those are y variables and this guy is z, now you can see the gene condition will hold true. And graphically speaking, the latent common cause for the y variables, which is L3, d separates y from z, right? So in this case, we can verify that, and we know, this latent variable d separates them. And as a consequence, we can also see the causal orders of the latent variables. By checking this condition, first of all, we can find the clusters, causal clusters by cluster. I mean, all measured variables sharing the same latent variables as parents. And after that, we can find the causal order of the latent variables. And if you would like to go further, you can estimate the linear coefficients, right? So now we are concerned with a linear non-Gaussian case. So all causal relations here are linear and noise from the non-Gaussian. And then we can just use the gene condition to estimate the latent variables and their relations. And right here, you can see application. We analyze the t-shirt burnout data. Here we have 28 measured variables. And on the right, you can see the hypothesized model given by experts. So by making use of a computational procedure, we actually recover the same latent variables, and we also recover the causal orders of the latent variables. It's very nice. First of all, you can see the hypothesized model given by experts is very good. They do not make use of data, right? They only make use of domain knowledge. They come up with this model, and it's consistent with the results produced by computational method. And on the other hand, you can see the computational method could be very useful if you want to recover the latent variables and their relations. And then we can go further. So recently, we try to recover the deep latent structure, hierarchical structure, by analyzing only the measured variables, as you can see from here. Basically, there are multiple ways to solve the problem. In one of the works, we make use of gene condition to recover the latent variables. And then by making use of the transitivity of the linear causal influences, we can just construct the latent variables layer by layer, okay? And in a different way, we can also make use of rank constraints to solve the problem. Essentially, we try to make use of low rankness constraints to recover the latent variables at the bottom level, at bottom layer, and then we can go to a higher layer and so on. And finally, the whole picture can be recovered. Okay. And here you can see a theoretical study. So in this work, we show the necessary and sufficient condition on the graph involving latent variables that is identifiable from data. So to give an illustration, on the right, you can see all those causal graphs involving latent variables that can be recovered from 3 measured variables. So in the first one, the 3 measured variables are independent. And right here, in this case, you can see there are 2 latent confounders. And x1, the measured variable, is actually the cause of one latent confounder, and this latent confounder is the cause of the 2 other measured variables, and so on. So in this study, the model is completely flexible. You can allow causal influences from latent variables to measured variables, causal influences among the latent variables, and influences from measured variables to the latent variables. But now we have the necessary and sufficient conditions. Then you can easily check whether this causal graph involving latent variables is actually identifiable. And here we assume that the model is either linear Gaussian or heterogeneous. So essentially we make use of non-Gaussian distribution or multiple distributions in this study. Okay, so to summarize, in the i.i.d. case, you could see that generally speaking, without making use of any assumption on the causal mechanism, we can recover the underlying causal structure up to some equivalent class. And if you make further assumptions, you can you may be able to recover the underlying causal structure uniquely. And even if there are latent confounders, this is still the case. You can recover latent confounders, and you can even recover the latent hierarchical structure from data. Now let's go further. So now let's consider 2 non-i.d. cases. Yeah.
There's about 10 minutes left, just to let you know.
Yes, perfect. Thank you. So in the first case, we have, by non-i.d. case, I mean, you can either have temporal data, time series data, or you can have multiple distributions. So first one is to just make use of the temporal information, right? Essentially, you can just even consider the method, granular causality, as a method of conditional impact-based one, together with the temporal constraints that cause cannot happen after the effect. You can even further incorporate instantaneous causal relations, right? So those works are rather classical. And let me just say a few words about this work. Here, let's consider, say, video data. Essentially, we have a high-dimensional time series, and the time series data was generated by a nonlinear invertible function applied to some latent processes. This nonlinear function is invertible and could be completely non-parametric. And for the latent processes, we have one constraint. There is no instantaneous relationship. So the latent process can be causally related, right? But there are no instantaneous relationship, because in the true causal representation, it takes time for causal inference to take place. We just assume that if the time series has a high enough resolution, there are no instantaneous relationship for the true process. And then even if the causal relation among those latent processes, ZIs, are completely non-parametric, we can still recover them on the very mild assumptions. Now, let me just use 2 examples to illustrate the results. So in the first example, basically you can see the kitty mask data right here. So it's a very simple data set, very simple video data set. Oh, I cannot see it. Okay. And from this view data with the image pixels as input, we recover the 3 latent variables. Is essentially one of them corresponds to the movement in one direction, a second latent variable corresponds to the movement in the orthogonal direction, and the last one corresponds to the size of the mask. In the second data set, we have 5 balls in different colors, and between some of the balls, there's a hidden spring, so they are related. And from such video data, we discovered 10 latent variables. Essentially, they are just the X and Y coordinates of the 5 balls. Now you can see we can recover those balls together with their relations from just the video data. So by making use of the causal principles, it is completely possible for you to discover the underlying objects and their relations in a completely unsupervised learning manner. Okay, so now let's see how we can benefit from multiple distributions with 2 examples. In many cases, we have non-stationary data. If you have long time series as time goes on, you can see the value of some background variable can be different. As a consequence, we have non-stationary data. In some cases, you collect data under different conditions, then you have heterogeneous data. So here, you can see the causal model can change. The causal inference can be stronger or weaker. And in some cases, the causal inference may even disappear. But basically, causal modeling and the diffusion shift are heavily coupled. Because if you have a causal model, because of modularity property, there could be diffusion shifts, and those modules, causal modules, must change independently. If you have data with diffusion shift, you can try to verify whether the changes are independent or dependent, and then you can try to infer the underlying causal model. So this is the idea. So in other words, we can benefit from multiple distributions in order to recover causal representation from data. So this is a particular work we did some years ago. Here, we are given non-stationary data or heterogeneous data. So we want to answer the following question. First of all, can you determine for which variables the causal mechanism change? So we can do so by doing conditional independent tests. And then, can you find the causal skeleton? Yes. Can you find the causal direction? Actually, here you can even benefit from the principle of independent changes, right? To find the causal direction. Because if you have wrong direction, then they will not change. The causal module will not change independently in the general situation. And finally, we can also find a low-dimensional representation of the change in the causal mechanism. So with some kind of kernel representation of the conditional distribution, we can try to find a low-dimensional representation of the changes. Here you can see an application to the stock market in NYSE, New York Stock Exchange. We analyze the 80 stocks. We can find the asymmetric information. So here we make use of only daily returns. And furthermore, we can recover the low-dimensional representation of the change in the causal mechanism. Actually, this is 2008 and this is 2007. We found that this curve is consistent with the so-called curve of TED spread, TED spread, which is a very complex way to measure the risk in the market. So you can see in 2008, the risk is very high and the last is long. And actually in 2007, the risk was already very high. Okay. Now, let me report another application of this method in domain adaptation. So in domain adaptation, we have some source domains and we have target domain. And we would like to make use of the information from the source domain to make optimal prediction in the target domain. How can we solve this problem? From the representation perspective, essentially, we would like to discover how the joint distribution of the data could change across domains. And then with this representation, we can try to infer the posterior distribution of the target variable or the label in the target domain. So basically, we use the augmented graph right here to represent the changes. And we can discover this representation by making use of method I just mentioned, called discovery from non-stationary data. And then in the target domain, we have this graphical representation and the values of the features, right? And then domain adaptation is nothing but the inference of the target variable given this graphical representation. So the principal way to deal with the problem of domain adaptation. Okay. Here you can see the results. By making use of this kind of hierarchical thing, you can see the performance accuracy is much better in the target domain. And by hierarchical thing, I mean, now you try to solve the problem by making use of multiple layers. First of all, from data, we can discover some qualitative information represented by the augmented graph. And then you can introduce the quantitative information to go further to make optimal prediction. Okay, and the point I want to make right here is that the representation you learn from data may not be causal without those assumptions. For instance, let me give one example here. In this example, Y causes X. You can think of Y as disease, and X as say, symptoms, and S as say, different clinics. So we assign patients to different clinics according to symptoms, right? And then if you consider the patients from different clinics as different domains, now you can see the distribution of Y given X will be the same, but the distribution of X symptoms would be different across domains. Then on the right, you can see the graphical representation. This representation is totally different from the underlying causal representation, right? So this is because here some assumptions underlying causal representation learning are violated. But for the purpose of adaptive prediction, this representation is good enough. Okay, the last thing, I will finish it within 2 minutes. So you can see that with the minimal change principle, we can discover causal representation from multiple distributions with the method CD node. And furthermore, you can see some other instantiations of the same principle. Let's have a look at the recent advances in nonlinear ICA with multiple domains. So this is the nonlinear ICA model. The measured variables are nonlinear functions of the underlying independent variables, right? So we know this is a classical problem, and we know without further assumptions, it's not identifiable. We cannot recover the underlying independent variables in a meaningful way. And then if you assume that distributions of the latent variables could change across multiple domains, and but you have a fixed mapping function G, then it is possible for you to recover this mapping function G and underlying independent variables. Now you can see on the left, essentially the graphical representation of the problem. Each latent variable Z can be influenced by some latent variable, so they can change. And then you only allow changes in the latent variables, but not anything right here in the transformation. So then you can show that any alternative representation will suffer more changes. You don't have an invariant transformation anymore. So as a consequence, you can recover the underlying representations. So we did some extension. We allow only a small part of the latent variable to change over time. And then we show that those latent variables can be recovered. It's very useful for domain adaptation. Why? Because in domain adaptation, you try to align the domains, right? By making use of some principles. Here, this is the natural way to enforce minimal changes across different domains. And then after you align the distributions across different domains, you can just easily do domain adaptation or image translation. Okay. To summarize, you can see a lot of machine learning tasks could benefit from suitable representation of the data, right? So if you make decisions or domain adaptation, clearly you rely on the underlying representation. And this representation would also be very useful if you care about recommended systems, trustworthy AI, explainable AI, and fairness in machine learning. And the second point is that causality is not really mysterious under appropriate assumptions. So we can learn causal representation or pseudo causal representation from data. So if you don't have those assumptions, you can still have the pseudo causal representation as a compact way to represent the data. So essentially, causality can be recovered under appropriate assumptions, even if you have a lot of latent compounders. Okay, thank you very much. That's all for my talk. Thank you.
Thanks, Kun.
Thank you, Kun, for the great talk. We got a bunch of questions, but for the interest of time, I will just mention one. This is about the nonlinear functions. So the attendee asks, since inferring the true nonlinear function might be quite a complex task by itself, how much does the estimation of nonlinear function hurt the causal discovery if the estimated model is not precise?
How much does the estimation nonlinear function hurt the causal discovery? Okay, so first of all, this is a very good one. Second of all, we should be very cautious because some methods do not rely on any specific assumption on the nonlinear function, right? And of course, finally, if you use a constraint-based method like PC, you don't really care about the nonlinear relations as long as you have a reliable conditional independent testing method. But in some other scenarios, you can see that if you do not assume the correct functional class, you may end up with something completely wrong, right? So suppose the model, the causal inference is very nonlinear, but they assume a specific functional class, and then it is possible that you estimate the wrong function, and as a consequence, it is possible that the estimate noise is dependent from the true cause. That's completely true. So as I don't have really a very good answer to this question because it is really practical, but you may want to start with some, if you want to make use of functional causal model-based method, you may want to start with a scatter plot of the distribution, right? You want to have a look at the distribution and try to see what functional class should be appropriate. And furthermore, you may want to start with some rather general functional class in order to make sure that you don't make mistakes because of the wrong functional class. Okay, I hope that's the answer to your question.
Great, thanks, Kun. All right, we'll move on now to Victor's part of the talk. So Victor, you should be able to share your screen now.
Thanks, Emma. So I will.
Yeah. Thanks, Kun. Yeah, so we started a few minutes late, so we'll probably end a few minutes late today. Sorry to the audience. Hopefully you understand and enjoy the talk. Okay, Victor. Oh, you're muted, but the slides look great.
Okay, great. Good. So, okay, good. So thanks, Kun. This talk was really like a high-level overview of causal representation learning. And so rather than try to discuss like individual subcomponents, I'm also going to try and just give like a incredibly subjective high-level view of what I think are kind of like some major challenges in this area at the moment. And hopefully that'll be interesting context for Kun's talk. Okay, so here is how I would summarize like the elevator pitch for causal representation learning, right? So this is the thing that I couldn't just spell it in detail, right? So the key idea here is that like the data that we actually used to train models was generated by some like real world processes that were generated according to some like physical causal mechanisms, right? So there's quite a lot of like actual structure underlying things. Right, and if we're a little bit clever, we can maybe learn something about that structure, right? More than what we get with just empirical risk minimization, right? So Kun showed a bunch of examples of this, including exploiting independence signatures, time information, or like some structural knowledge about the processes, right? And of course, this is like a lot of just causality, and so the distinctive thing about causal representation learning is like what you're trying to learn about that underlying process is like both some high-level causal variables that summarize like the things that actually show up in the graph and something about their like causal relationships. Okay, and then the point of all of this is that hopefully by going to the effort, doing some extra clever things, you get out some like desirable behavior for your just vanilla machine learning systems, right? Like causality is not the goal; it's a tool. It's supposed to accomplish something, right? And the normal stories that people tell about this are robustness of machine learning systems, sometimes something about explainability, and I'm just going to mention this as a throwaway, but there's also some interesting work kind of arguing that trying to do this causal representation learning thing can also be helpful for like the sort of more old school task of just like estimating causal effects, right? But so this is like the high level story. And then the question is like, well, okay, how well does this story hold up, and what are like the major open problems here? Okay, so let's zoom in a little bit on domain shifts because it's an area I've worked on some, right? So the hope in the domain shift literature is that you use some knowledge about the causal structure, and then you get robustness over domains in the sense that, I take some predictor, I deploy it in a new domain, where a new domain means like a new hospital or something in medical data, and then I do better. Right. Okay. And roughly, and so this is folk wisdom maybe, but roughly on real domain shifts benchmarks, so in like benchmarks that were constructed by people who were just sort of like, we want to get like very realistic data, right, and then see what actually happens. The conclusion right now is like no existing domain shift method beats, at least consistently beats, vanilla ERM. Right, and that's even like a good faith interpretation where it's like, if you think hard about like which domain shift methods to use, right, it's still like there is no practical guidance that like lets you do consistently better, right? In fact, state of the art as it is just find methods that used as much pre-training data as possible, go as big as possible, and just use the dumb big thing, and that's your best bet in general. Right, and so a particular consequence of this is like, at least in this context of like these sort of realistic domain shift benchmarks, there's no clear win so far from causal attacks, despite the fact that we have now like a decade of causal attacks going through. Okay, and so question is, what's going on here? That question's too complicated to answer in 2 minutes, but here's a particular flavor of direction that I think is maybe profitable. Right, so I think a lot of the work in applying causal ideas to the domain shift problem is predicated ultimately on the idea that what you would really, really like to do is just know what the actual causal parents of the thing that you're trying to predict are, right? And then if you just knew the causal parents of the thing that you're trying to predict, then because causal relationships are invariant across domains, you could just always rely on the parents, and you would have some kind of like minimax guarantee on the performance of this thing, right? And so, right, there's work on this dating back for quite a while, and indeed, like the logic here is sound, the math works out, it's great, although as I say, empirically doesn't seem that useful in practice, right? Okay, so one possible gap here, is that the motivation for this kind of work is we say, well, let's consider the case where causal relationships are stable across all domains, right? And any domain shift is just due to some kind of like spurious association due to like shifting distribution of unobserved confounders in the data, right? So just like, restrict to this simple case where it is like structural relationships are fine and you observe everything that you would need to sort of disentangle spurious and non-spurious relationships. Okay, so an observation here. So this is a figure that one of my students made. An observation here is that basic like English statement, like stable causal relationships and domain shifts due only to spurious associations, is actually consistent with a bunch of different causal structures, right? And so I'm not going to explain this figure because there just isn't time, but the point here is like, under some natural formalization, you can say here are 3 different classes of causal structures that are consistent with this basic causal model. And the observation here, the important observation here, is that in general, that setting where it's sensible to predict Y from the parents of Y only holds in one of these causal structures, right? So that there's only actually one special case where the desiderata of use only the causally relevant features, right, is somehow maps well to the case of predict Y only from the causal parents of Y, right? So I mean, the most obvious exception is just like when Y causes X, right, the anti-causal learning setting, right? But there are more like complicated exceptions as well. Right, and then an issue that we see here is like, well, the sort of causally correct thing, the thing that doesn't use any spuriousness, actually doesn't in general have a nice relationship with robustness across domains, right? And so in particular, it's only actually unambiguously the correct thing to do in like that one special structure, right? And in other settings, just kind of like using the right causal structure will not in general just automatically lead to robustness. So I put a paper link here for some like negative results of this flavor. But you know, the sort of high level point here is like actually the story, which is just like learning the underlying causal structure to getting good model performance, even robustness, is actually quite complicated, right? Like it's not just going to be an automatic thing. And I think like probably the community as a whole needs a little bit more attention to that. Okay, I'm going to take 2 more minutes, if that's okay, just to say something about the second thing. Okay, so this is a total non sequitur, right? But like I think like a question that is on the minds of a lot of people working in machine learning right now is what's up with scale, right? And so in particular, there's this emerging paradigm where like we're seeing amazing performance from like very flexible models trained on extremely massive data corpuses, right? And in particular, these are models trained with objectives that are not doing anything clever causally, right? So we in fact do in some sense the dumbest possible thing. Right, so for language models, the way that we train right now is just word by word in a document, try and guess what the next word is. Right, that's the objective. For vision, it's basically you just take pairs of images and captions and try and guess which caption goes with which image. Right, like that's the training objective that you use to get at this structure. Right, so absolutely no causal knowledge. Right, but in a sense that I'll make precise in just 1 second. These things actually seem to recover like pretty deep causal understanding of the world, right? They know all sorts of like relationships that appear to be causal, relationships, right? And so there's like a funny tension here, right? Because there is the sort of Pearlian view. Actually, I don't know if he still espouses this, but as recently as like a few months ago, right? Pearl was taking the view that if you just are like naively learning statistical signal, right, it's fundamentally impossible for you to recover like true causal structure, right? But empirically, just like doing these things at scale seems to actually be like getting them automatically, right? And so there's like a real tension there. A particular instantiation of this tension is this focusism that I mentioned earlier, that just doing this like naive at scale training is actually the best option to get like robustness to domain shifts in reality. And so a particular question here is like, all right, why is this happening, right? So is the Pearlian view just wrong and like actually we will get causal structure automatically, right? And if it is the case that we don't need any particular cleverness, like just going with scale is getting us a lot of causal structure, like what's left? What are we still hoping to gain by thinking through this causal representation learning paradigm? Okay, so I'm going to end on this slide, but just to give in sort of concrete example of what I mean. There's like an old school like cutesy example of reliance on spurious correlations in machine learning, which is you train a classifier to distinguish cows and camels, right? You see a bunch of cows in grassy fields, you see a bunch of camels on beaches, or so you see a bunch of camels on deserts, right? Then you go into a test environment where there's a cow standing on the beach and your classifier incorrectly identifies the cow as the camel because it hasn't disentangled the concept of object and background, right? So old school cutesy thing, right? It won't surprise you to learn that if you ask DALL-E 2, so this is an image generation system, to just generate a picture of a cow standing on a beach, it has absolutely no difficulty doing that. Right, it certainly is automatically learning to disentangle background and foreground, but actually it's doing a lot more than that. So here's an instance where I asked the system to generate a purple cow playing saxophone on Mars. And the main point that I want to make here is that it succeeds in doing it, right? So it certainly has never seen an image like this before, right? But it has some kind of like complex causal understanding in that it knows what a cow is, it knows what it means to make it purple, it knows what Mars is, it knows how saxophones relate to cows, right? There is some kind of like a much richer structure here than like the old sort of like toy models would have suggested. But there is an interesting bug here, right? Which is like all of these images are cartoons, right? And it's not obvious. There's nothing clearly in the prompt that said that I wanted that, right? So there is still some kind of like weird data correlation at work under the hood, right? So the problems are not totally solved, I do think like maybe this is a call to arms to just say we should take more seriously that in fact actually just doing the dumb thing at scale is getting an awful lot of causal structure, and we should really make an effort to like understand what's going on there. Okay, cool. So I'll just stop there, I think.
Thanks, Victor. All right, so we are definitely out of time, but I think it would be nice if we gave Kun a chance to kind of comment on the discussion. So feel free, Kun.
Okay.
And also thank you for answering so many questions in the chat. I will say also that all the questions that were not answered will be passed on to our speakers, so don't be concerned about that. All right.
Oh, that's great. Okay, I was worried. Let me give a very quick one. So first of all, regarding domain adaptation and causal representation learning, I do not think the two things are really related to each other. At the beginning, some methods, some domain adaptation methods were inspired by causal thinking, because with the causality, very often we say, oh, this is stable, and that part could be very sensitive to a lot of other factors. But in terms of methods, they are not really related. First of all, for domain adaptation, you only care about how the distribution changes. And that's why I gave example to illustrate the difference between the graphical representation you use for domain adaptation and the causal representation. And right? And we cannot just say, oh, this is a causal model, and then I can just do domain adaptation based on that. And we cannot say causal features are more stable. Even if X is the causal Y, right? It's completely possible for the causal influence from X, Y to be very sensitive to a lot of other factors across different domains. And but in domain adaptation, we really rely on some compact representation of how the joint distribution can change. We can discover such information from data, right? And then we can make use of it. You know, causal representation learning is possible only under appropriate assumptions. So this is the response to both the domain adaptation part and also the causal learning part. Very oftentimes, those assumptions may not hold true. As a consequence, we cannot really learn we are not sure that the learned representation is causal. But if the purpose is not really a causal problem, then totally fine. But if you really want to find a way to do optimal intervention, clearly you care about those assumptions, and maybe you want to check whether those assumptions hold true in the first place, right? So to summarize, domain adaptation or transfer learning is not really causal problem. They could be very different, and the representation you can use for adaptive prediction could be totally different, although intuitively they are consistent at some level in many situations. And furthermore, please pay more attention to the assumptions underlying causal discovery or causal representation learning, because without checking those assumptions, you may just end up with wrong representations. Okay, so Victor, is that a fair response to the points you raised?
Yeah, that's interesting because you went even more negative on the causality domain shift thing than I would have. So my position is just that the relationship is complicated, not that they're disjoint. But yeah, I don't find myself strongly disagreeing with the things that you're saying. And since we are 11 minutes over time, maybe I'll let you have the last word there.
Okay, cool. Thank you very much. That's all. Thank you. And I will continue answering questions. Yeah.
Well, we'll actually kind of wrap up the seminar now, so you may lose the opportunity soon to finish answering questions. But again, we will send all the questions to Kun. If you have further questions, please feel free to continue the discussion offline or online, but not in the seminar, I guess. Okay, just 1 second. Right, before we finish, I just want to say thank you again to Kun and to Victor for the nice discussion and the presentation. Kun, thanks for giving us such a big overview and actually answering a lot of questions in the chat in the meantime. And Victor, thank you for an interesting discussion of kind of the issues that arise in some of these settings. Next week, we'll have a talk by Luke Meritrix from Harvard on a devil's bargain. So something that would have maybe been more appropriate for this Halloween edition, but a devil's bargain, repairing a difference in differences, parallel trends assumption with an initial matching step. So hope you all join us for that discussion. And sorry to run you a little bit over time. And have a great rest of your day.
Thank you very much, Emma.